Thank you for coming and thanks for tuning in. I'm Andy Warfield. I'm the CTO and a co-founder at Coho Data. And this is part 2 of 4 talks in our SFD 8 presentations. And in this one, I'm going to tell you about the architectural anxiety involved in building what I'm going to describe as a medium-sized storage system. So this is an interesting sort of lesson from the year that we've had. So for all of these next 3 parts, I'm going to try and do a little bit more of a careful presentation thing, which is that I'm going to tell you an interesting thing about the system up front. I'm going to summarize what I do at the end, and I'm going to completely go into the weeds in the middle, right? So in previous talks, I've just gone into the weeds. So this is me trying to restrain myself a little bit. So there are 3 sort of interesting aspects of the system that I want to really clearly articulate to you guys. The first one is Coho's architecture uses a mix of different types of storage media, right, to build a storage system. We have hybrid boxes that mix NVMe flash and spinning disks, and we have AFA boxes that mix flash and flash. These things can be combined, and our job is to have you not think about these as a customer, right, that you should just have great storage performance and scale.
They can be combined within the same cluster?
Yes, they can, and they're getting better all the time in terms of the way that we integrate and scale on them. So the current product offering does that. It allows you to mix these in the environment and use them as a single storage system. As I explained earlier, we use enterprise NVMe for our primary storage. So all writes are serviced by NVMe, right? They age over time and then are pushed out to slower tiers of storage, right? Reads are served from them. The way that I think about NVMe in the platform is that these faster types of storage should actually house data that is like weeks or months of recency, right? That the data that you access over any kind of like long-term recency should be there. And it's really like lukewarm and cold data, right? Tepid data that goes off to these other forms of storage. It's important to realize inside the product that, as I've talked about in the past, these flash devices are so fast that they overwhelm connectivity, right? And I'll talk about this even more later, but the product architecture then is based on this model where we have one NVMe device that's capable of saturating a 10 gig NIC, and they're plumbed through directly, right? And we tie a CPU to that, so we're in a single port backing it by a really, really fast storage device that can saturate the port. And so this gave us this distributed systems problem because we had to add a port every time we added a device. And so, suddenly we're building a distributed system. And so what Coho did was we brought an SDN switch into the platform, and we abused the interfaces on the SDN switch, specifically OpenFlow, to present a single IP address, right? We transparently scale NFS, or whatever protocol target you want, to function as a cluster resource across here. Does that make sense? So this is like kind of one of the neatest things that we initially did, was one IP address, one data store that you configure. As you add storage, right, we balance the connections in the data, right? So when you add a second box, you're plugging in 4 more 10 gig ports, and you're doubling not just the capacity of the system, but the controller compute capability and the data path into the system.
I have a question on that. Yeah. One thing I've always wondered about Coho is the extent to which you're reliant on the performance and the stability of the internet, the Ethernet switch that you're using to interconnect the nodes. Because it seems like a lot of storage people, and I'm not accusing you because I know that you have a different background. A lot of storage people assume that networking is sort of a black box and it just sort of works. You buy any switch, you plug some stuff into it, and you're good. But networking people know that that's not the case, and that there's a lot of variability in terms of network switch performance and quality and reliability.
Absolutely.
Can you talk a little bit about that, or do you have a section that you want to talk about that?
No, I'll talk about that now. That's true that storage people frequently make that assumption. But then if you go to any large traditional storage vendor, they often have somewhere a 150-page manual that talks through all of the different Ethernet configurations that you're going to have to deal with in the universe. Right? The networks end up being incredibly difficult to work with.
That's why we like Fiber Channel.
Because Fiber Channel is super easy to work with.
So all you guys need is for Brocade to come out with an OpenFlow enabled Fiber Channel switch.
Awesome.
And then we're in business.
Open Fiber. I can't wait for that. The switches. So there's a few ways to answer the question that you asked, Stephen. It was around the sort of like network stability and complexity of things. First of all, you see every single insane possible network configuration in the world when you start deploying into these things, and we have had to add an enormous amount of support for that over the past 3 years. Initially, we did all of our connection tracking based on source MAC addresses because that was sufficient for what we're doing in these environments, but it demanded that we do source MAC hashing on the upstream switches. Customers don't want to change that stuff, so we had to support all of the different ways that you configure traffic distribution across lags and stuff like that, right? As we worked with UCS environments, UCS does things differently, right? All of these different things come into play. On the switches themselves, from the beginning, we've worked with Arista. We early on tried to qualify a bunch of white box switches, and at the time when we started, right around 2011, the white box switches were incredibly flaky. to use a really technical term, right? They often came with a Linux install that would not actually boot. And so they were very difficult to get as far as even doing OpenFlow programming on because they just wouldn't boot, and we'd send them back and then we'd get a new version. So more recently, this has really changed, and we've been working with a few other switch possibilities internally, certainly around this. I mean, the ideal for me is that this moves to the point that you buy whatever switches you want and we just integrate against them. So
do you sense a future time when the Ethernet switch will be part of the sale from Coho?
The Ethernet switch today is part of the sale from.
But that it'll be part of, I'm sorry, you're right, yeah. That it'll be part of the product, like really packaged in, not, like an integral part of a storage system. Because most other storage solutions, they'll maybe sell it as a bundle, but... Oh,
no, so let me be really clear on that. Today, the software that we actually build and sell, the thing that we configure and ship, all of the complicated stuff today actually lives on the switch at install time. These things are just basically Pixie booting boxes, and the switch programs them, right? It does the OS install onto these boxes. So then all of the moving parts actually end up living on the nodes. But from a delivery perspective, the switch is completely integral to the convenience of how we deploy. A lot of the complicated moving parts move down onto these boxes because they have much better CPUs, but the switch is still very intimately involved in everything that we do in terms of traffic management.
But not to be pedantic, the switch isn't orange.
The switch is not orange, yes.
And you know what I'm trying to say. It still seems like it's not, a core part of the product. So it still seems like a thing.
I love this question. So Arista won't let us bezel their switch.
Okay.
I think if we sell a few more, they'll be arm twistable into it. The white box.
So every system comes with a can of orange spray paint.
Exactly.
So I can do it myself.
Spray paint. Just cover up the holes before you do it. So, anyways, no, so if that's the benchmark for integration, then.
Well, yeah, I'm just trying to get to the point where instead of a bundle, it's a product, a single. I buy a car from Ford. The radio says Ford on it. It doesn't say, Delco or Sony or actually. Mine does
some of them
Sony.
actually.
But the point is,
it really doesn't say Delco because that's GM.
Yeah. But yeah, I hope you know what I'm trying to get at.
I think I get what you're saying. I mean,
it still seems like it's not there.
From our build ship perspective, this is qualified and assembled as a unit, and it goes out like that. So the only thing that is short of what you're asking for, really, like the way you're describing this is exactly how I look at the system today, right? The only thing that's short of that in terms of what's really visible in the rack is the lack of a bezel. And, we'll sort that one.
Well, no, we really want the 40-port switch built into each
server node.
Into each server node.
We actually looked at that very early on. We looked at fabbing servers that had an integrated switch in the back, and the decision was that the price and speed to market for that was slower than what we could do this way.
Yeah.
So to that end, are you seeing your customers plug into your switches or plug their switches into their
We see both things, and
networks?
it's about 50-50. It's a good question, right? So in some cases, we see direct connection. Customers are installing these and then wiring their clients directly into it, and in other cases, there's an existing switched infrastructure, and they're running lag over it, and then they plug into us over that.
How much of a challenge are you finding when people try to integrate their own networking rather than using the Arista switches you provide?
So they still use the Aristas, right? So we still use, because the Aristas are where we scale our boxes up.
Got it.
I would say less and less. That was a place of integration where we had to do a ton of work over the first 2 years, right? Getting through all of the different environments.
Okay.
So let me come back to this point. So let me talk about medium-sized storage for a second. So this is a homage to medium-sized things, right? The Chevrolet Cruze. And so I have a bone to pick here, which is that the reason that I'm saying medium-sized is that, and I'm guilty of this as well, that early on in talking about a storage architecture, we did this hand-wavy thing where we said, Google and Facebook buy a pile of white box servers and build a big cloud storage system. And so we're going to kind of do that. And we're just going to package it, right, for consumption in the enterprise. And it turns out that when you are building a storage system for 1,000 or 10,000 or 100,000 nodes, you do a bunch of stuff that just doesn't work when you're building a storage system for 10 or 100 nodes. And so the idea that you're going to take any of these techniques, and a lot of the techniques are published and well understood, and apply them at a granularity or at a size of like 6 racks, right, or even tens of racks, is patently absurd, right? As an example, in the Facebook warm blob storage paper that was published in the last year, which is a really cool paper, and you should go and look at it, in that system, they're provisioning storage at a row of racks, right? At the end of that row, they have some dedicated servers that are responsible only for doing erasure code parity reconstruction, right? When you lose some disks, there are servers that are provisioned to do just that, right? When you're building stuff that's like many, many racks, of course you can do that. You can do all sorts of crazy statistical things around placement because you have large numbers on your side, right? There are other aspects to this that are really important to think about on that domain, right? One thing that is totally missed in a lot of those conversations is that when you're doing OS development, right, which is a world that I kind of grew up in, there's this notion of a red line, right, in the OS. And the red line is the syscall API, right? It's the place above which you are not allowed to change anything, right? So you are hamstrung when you do OS work in that you can't do anything cool above that line. So you have to do all cool things sticking to those rules. And this is absolutely true in a data center environment, right? So when we install into these customer sites, right, legacy OSs, legacy application code, I can't change it. It's often VMware, it's often OpenStack. Really inconvenient storage protocols in here, right? Things that are like, 20 or 30 years old, NFS v3, iSCSI and HDFS, right? All these things have newer versions that are supposed to be better, but are not getting deployed and won't be deployed for years because there's still these legacy clients. And so below this red line, I have to deliver awesomeness, right? This is my mission, right? And these are the sort of bonds that constrain my ability to do it, right? And I'm going to carefully and in a very Canadian way constrain that notion of awesomeness to a Chevy Cruze or similar, right? I don't want to get too far ahead of myself. And so this is another thing that isn't true in those large cloud environments. So when people say, like, we're doing cloud storage, we borrowed what Google did, they pioneered, and I'm building it, it's totally nonsensical, right? Solving a different, interesting, and potentially even harder problem to do this at the scale that we're doing it. They get to change the applications, they get to place over thousands of nodes, right? Just totally different. Okay, and so, as I've said, inside our product, right, OpenFlow, SDN Tor switches, and then dynamic chunk placement and a notion of topology below it. And so, there I go. Okay, so now, the diamonds part. Let me come around to this. So I'm trying to like slowly, sneakily tell you about our product and then kind of come back to much more broad things. And so now let me do a little bit of this broad thing. So I can't seem to give a talk without putting a picture of a PCIe card in it. I find them very relaxing to look at. This is Intel's P3700. It's a really great example of a commodity PCIe card. This is Intel obliterating all of the higher cost proprietary PCIe cards that came before it and selling something that performs more predictably and costs a tenth of the price. It's still a pretty expensive card, right? These things list in their largest capacities, which is between 1 and 2 terabytes at around $3,000. Right, and this is a really, really sort of subtle and important reality.
That's not so expensive compared to the $20,000
yes,
Fusion IO
absolutely.
card.
Well, the Fusion IO had a CDW listing that you could go to on the web for the Onyx that was $1 million. Right, you could order it with your credit card. I was always like desperate to do that. So with someone else's credit, with Howard's credit card.
I don't have $1 million credit limit, Andy.
The thing that I want to mention here, and I don't think that I've characterized this to you guys this way before, and I think it's a nice way to think about it. When we were working on Zen, right, when I was a PhD student and we were building that system, and we were doing virtualization, one of the strongest arguments for it, and there are only 2 real arguments for doing the virtualization thing to begin with, but the strong one, right, initially was one of efficiency and utilization, right, the financial argument, right, that basically the servers are idle all the time, And if you look at the price of the component parts inside that server, right, you have this like 1U box and it has 2 sockets, and each of these sockets costs $1,000. So you've got $2,000 in chips, and the rest of the enclosure, including RAM, motherboard, and everything else, costs about $2,000. Right? So 50% of the COGS on that server is the CPU. And now this thing costs $3,000. Right? And you put 2 of these, let's say, inside this box, and suddenly you're in a space where the flash or the NV memory costs half the price of the system and pushes the CPU onto the other side. So if you're thinking from an economic perspective on how to design your data center, stop thinking about the CPU. It's the wrong thing to optimize, especially if it's virtualized. And so this really confuses things from a storage system design perspective. That's why these things are effectively diamonds, right? Diamonds are expensive, precious, and hard to divide.
But pretty.
But pretty, which is why I like looking at them, right? I like looking at this one more, right? And so
You're a little weird.
So let's think about this, because this is the point, and I struggle to make this point more clearly, and I think I get better at it every time I present to you guys. But you could build a single monolithic storage system out of these things. Today, my math says that if I used about 24 PCIe lanes for NICs and 24 PCIe lanes for these things, I should be able to do about 5 million 4K IOPS in a single scale-up, not scale-out storage target. And that thing would need something in the neighborhood of, I think, about 200 gigabits per second of access bandwidth. Right? And you would have a heck of a time plumbing connections to it. Right? And it would be a really expensive box. Alternatively, you could go and stick these in all of your servers and just not use them, right? Because the amount of work that you have to drive to get the $3,000 value off of these things is quite a bit. And the thing that we see in a lot of cases where people are doing server-side work with these is they just can't drive the load to make it value win, right? And so the reason that I'm talking about rack scale convergence is I want our customers to be able to buy as few of these as possible and buy them over time and keep them as busy as they can, right? Which is why I'm using all of the tricks that I learned virtualizing the CPU, right, to virtualize these. And so that's kind of where this comes from. Now, that I said that there were 2 wins, 2 arguments for the CPU virtualization thing, and both of them actually hold here too, right? The other win to virtualizing the CPU was once we started to build successful hypervisors, you stopped letting people access the server hardware directly, and in fact, the server hardware became effectively invisible, right? You took those out of service without telling anyone that you were going to take them down. Right? Same thing should be true here, and it's not today, depressingly, right? You plan for massive data migration downtime, right, at the time that you buy a storage system in many cases. And so, let me put some numbers behind this. This is the memory hierarchy of my childhood, and given that I was teaching this memory hierarchy to third-year computer science students a few years ago, my childhood only recently ended. But anyways, right, the model was the one that I described before. You have 3 types of effectively processor-side memory, right? Registers, caches, and DRAM, right? They're really, really fast, pretty expensive, and they're good, and then just don't ever, as a developer, write below that, right? Don't persist stuff because it is super painful. And so this is the memory hierarchy that I'm still struggling to come to terms with, right? This is the thing that I think about at 3 in the morning, and it drives me crazy, right? When we started working with PCIe Flash, it was an enormous challenge for me to start to think about the software consequences of these devices that were so performance dense. And we built a system for them, and we finally started to come to terms with that, and now we're seeing these NVMe memories, right? The 3D crosspoint that Intel is talking about, that are 10 times lower latency. Right, even than those, right, that are basically 5 to 8 times slower than DRAM, and 5 to 8 times higher capacity, right? The thing that is really important to realize about this list of memories is they're not better than one another, relatively speaking. They're interestingly different. And so as a storage system designer, I need to figure out how to combine them in ways that are valuable, right? And I need to figure out how to hug these curves as they fall over time. And so there are 2 really, really crucial observations that I've drawn from working with these memories over time, right? And these are like really interesting things to think about storage system design under. The first observation is that the forwarding decision times in a storage system, and I'm using a networking instead of a storage term here.
D stage?
Pardon?
say?
Just request processing, let's say. So a request coming in off the network that's a read or a write, from that request being passed on to some number of disks, right, and being replied to, those times are becoming shorter and shorter and shorter in a terrifying way, right, to the point that the tricks and methodologies that you have to use here in a storage system today look a lot more like building a high-speed middle box or router, right, than building a traditional storage system. The second point, though, is when I had a small NVRAM-based write buffer, right, or a small RAM or flash-based cache, it's hard to screw it up, right? It is such a small fraction of your aggregate storage that you just have to keep the hot stuff in it. And so we had ideas like LRU, like at least recently used, where there are refinements on it like ARC and CAR, right, as better caching strategies that tried to like do the right things. But really, right, it's pretty straightforward to keep the hot stuff in there. When you are dealing with gigabytes and terabytes of expensive storage, right, the time horizon that you're trying to optimize over is bigger, and it serves you very well to think harder, right, about how to manage the stuff that's inside there. And so,
and indexing becomes an issue.
yes, metadata overheads, right, all that stuff ends up being, so these are both really interesting sort of.
When you're talking about forwarding decisions, you're talking about the time to access the storage or the time to get to the data to the point of storage? The latency of the storage device or the latency of the controller providing the information to the storage
I'm saying that as the latency of the storage device itself falls,
Yes.
the latency that the controller has becomes more significant.
Yes.
Right?
Yes.
And so it has to be more and more careful. Okay? And so I'm going to mostly talk about the first one of these, and then I'm going to go into the second one in the next talk. So I've used this in a couple of talks recently. I think this is a really nice way of conveying exactly what I'm talking about. Right? This is a graph from the guys at Intel that run the DPDK. This is a software library for building high-speed switches, right? Software switches. And they're talking about how much time a processor has to process a packet, right, over the generations of Ethernet. And so what you see is with fast Ethernet, right, with 100 megabit basically Ethernet, you had like, 7 microseconds to make a forwarding decision. And over generations, this falls to the point now where it's effectively on 100 gig, 6 nanoseconds, right, of processing time.
So if 100 gig did CSMA CD, the maximum size of the network would be 8 feet.
More or less.
Right.
I think it would be 3 feet.
Don't distract me. let me show you the storage line for this. Okay, because the storage line, what I'm gonna do now is I'm gonna superimpose storage over the same period of time, and I'm just gonna adjust the y-axis because the storage one starts a little bit above here, right, just to fit it in. So here's the storage one, right? That graph is this one.
Yeah.
Right? And this is storage. And it's important to realize that we all know that disks suck, right? So even if we take this off, right, this is self-similar all the way down, right? Like the move from SSD to PCIe to main memory is a significant drop at every stage to the point now that we're in the same ballpark, right? That the storage decisions on these devices are DRAM level decisions. And so, another graphical way of characterizing this is old storage systems look like this. I had a CPU that was not working very hard talking to a big pile of disks. And today, to work with even a single device, I need a pile of CPUs, right? I need a pile of cores to actually drive. This is a hard problem. Let me give you some graphs, right? So in the networking world, working with, so that example that I mentioned in the last segment about the work that we did with Intel and UBS is actually a 40 gig system. So we built it on top of 40 gig networking hardware and all flash. It was, like I said, it was a reference architecture, and we were looking at some new hardware. This is a graph that you see in a lot of high performance networking papers to characterize the pain of working at high bandwidths, high traffic rates. And what you see is at 4K, which is more of a storage style, request micro benchmark workload anyways, you have to add cores, right, to get up to link saturation, right? And this is just trying to interact with forwarding data across a pair of ports. And if you go to 1K, it's so clearly CPU dominated that that's what happens, right? And so, the way to think about these graphs is at these points in time, there's no CPU left to do anything useful. Right? And so you need to get far enough into this regime that you can actually go and build whatever application you're trying to build.
Are you saying the storage devices are becoming CPU saturated?
Well, so let me show you the storage device. Right? This is that NVMe that I showed you the picture of before, and I'm using a queue depth of 8 on these things, right? So I'm trying to save a little bit of space to do some compute on them, right? So I could saturate that device with one core, right? I'll be really clear about that, but it is full bore, right? Nothing useful happens there. So I've scaled down its queue size to 8, which is still pretty ambitious looking at a lot of workloads today. And so I'm putting a steady state dispatch of 8 requests per core, and it takes me, right, 4 or 5 cores to saturate the P3700, right? And this is characteristic of a lot of these NVMe devices. Right? And the way to think about this again is if you actually have to go and implement a storage system, right, like a file system or whatever, that lives up here, right? It lives in the slack on the CPU that's doing this. And so you actually need way more cores than this to keep the device saturated. And
not to mention hyperconvergence, where I'm actually going to try
so
to run real applications.
This is the anti-hyperconvergence kind of illustration, right? That it's just, you can't run useful application workloads, right, on that system to saturate these devices, right? They're just, except for maybe like 2 applications.
Can I make one point though? I mean, I like hyperconvergence. I like traditional storage. I think there's use cases for both.
Yeah.
I don't think that hyperconvergence is necessarily about maximizing resources.
So this is, yes, I totally
absolutely
agree.
about
Yes,
ease,
yes. And so let me back away from that. I am not saying hyperconvergence is BS, like don't do it, this is a terrible idea, right?
Right.
Right. Like
No,
same thing with my
if you
public
don't
cloud
if you don't have
plan, right?
nearly enough demand to keep a P3700 busy anyway,
Yep.
then it makes perfect sense.
Yes. Yeah, exactly. And
It's
arguably
it's the ultra high performance hyperconverged intersection I object to.
yeah. I think that's fair.
You mention cores all the time, but you actually don't mention megahertz of each single core, because probably it doesn't matter.
It does vary a little bit, but it's kind of in the noise relative. The shape of the graph is still the same, right? And the cores aren't getting appreciably faster. Yeah. So I'll show you one more thing, just to really kind of hopefully drive this home, is these workloads are shared nothing, right? They're just generating work, right? And so storage systems are all about shared state. And as soon as you add any contention inside here, right? So this is an uncontested lock, right? This is the same workload at 4K, right, over a 40 gig link, and it's just occasionally taking an uncontested lock. And one uncontested lock results in this massive drop in performance. And so the system is so sensitive to sharing of data across cores that this is a big design concern. So I think the point that I'm trying to make here is that the design work that's involved in storage systems is becoming a lot more complicated, right, with this new hardware. And it's something that actually is like years of work to get right? It's not just something that you set out to do, and get right. And so the final point on this, I think, is this one. Like storage data paths are like network data paths in hell. But this is, I've built network forwarding systems, right? I've built NATs and switches, and I've done quite a lot of work in file systems. And when you're working at these rates, right, in file systems, you don't traditionally worry about performance as much. You worry about on-disk layout like crazy. You worry about how many accesses you have to take to do snapshots. Or you worry about scanning for dedupe, interfering with production workloads. But you don't worry about like a lot of locking and concurrency control on the active data path. And here you do, right? And unlike networks, right, everything is still in address translation, right? But you have to track the reverse direction on all requests, right? You have to acknowledge things. Requests split up like crazy. There's tons of opportunities for contention, right? This is just super hard, right? There's the whole point of the slide. It's just like the complexity of doing these things the networking people have never seen building networking. And so storage is becoming a crazily difficult and interesting systems problem.
You're talking at this from a perspective of bandwidth issue, but the latency across like Ethernet and stuff like that is never. I can't see it approaching the speeds of fiber channel and things of that nature. But
I'll come back to that. Well, so I mean, here as a
bandwidth perspective, I understand what you're saying.
No, so as a simple example on that front. This is a model, right? And I'm not going to go too much to that. I am like super in the weeds now, so I'm going to back out in a couple of seconds. But
We like weeds.
This is an example of work that we've done with Intel around the DPDK and the more recently announced Storage Performance Development Kit, the SPDK. And that model of stuff is basically that you have a physical NIC and a physical NVMe device, right? And you have virtual hardware queues to these things that allow you to tie those to a single core. And so packets coming in go to user space to a core and go down to a device. It's designed around avoiding contention. We built effectively all software RDMA implementation on top of this to measure what we could achieve in terms of user-to-user TCP round trips. And it's 13 microseconds, right, user-to-user. And so this is in the same range of a lot of non-volatile storage. right? So it is certainly possible over Ethernet, right, with these technologies to do stuff in that range. Now, this isn't the only way to do this, and in fact, this is kind of a distracting aspect of looking at these things, right? The bigger challenge is really how to solve all of the higher level problems around building storage. I just wanted to emphasize that there's a lot of work going on to try and get there. And so, how am I for time here? 10:30. I'm doing pretty well. So I'm going to show you one thing really quickly on the whiteboard, if you still are up for it. If you guys want me to stop, right, and go into the next section, I can. But I thought I'd kind of give you one sense of where things are headed for us. Okay, so I'll take the scary Clockwork Orange pictures away, and so let me just sort of explain a thing. So in the product, we have a notion of a controller, and I talk about this at the beginning of the next section as well. But basically, you have a bunch of these boxes, right, that have some amount of flash and some amount of disk. And then you have this sort of SDN layer, right, that has all of the client connections coming in and being steered off sort of appropriately over these things. And there's bits of data, right, that reside, right, on these various areas. And one of the things that's kind of really unique and cool about the way that we've built storage at Coho is that on the side of this, I'm going to draw it as a brain, right, there's a controller. Right. And this controller is a controller in the software-defined networking sense of that term, right? It's a thing, right? The idea with SDN is rather than having your devices all implement some sort of convergence protocol like BGP or spanning tree or things, right, and kind of come to agreement on their own, right? In the SDN world, the controller looks at the whole environment and makes decisions on behalf of all of the elements. Right, and it's been successful in enterprise networks because you control all the elements, right? Less so in the sort of whole internet space where there is much more heterogeneity. And so our controller actually has an SDN, right, component to it that actively steers these connections, right? And so one of the knobs, if you will, that our controller has is it can look at all of the clients coming into the storage system, right? It is aware of the load on the client sessions and ports, and it can transparently move those connections around at a very fine granularity, right? It can basically migrate connections whenever it wants. You see one IP address, right? One IP address up here, and it just scales transparently across everything, which means that when you go and add another set of nodes to the system over here, it's able to add those links and migrate requests onto it, right? This is how we scale out the sort of access bandwidth into the system. This controller also knows about data. And this is its other knob. And so underneath here, it is able to trigger migrations of these things from one location to another, right, over time. And so the controller is continuously basically solving a satisfiability problem in the cluster. It's looking at all of these sort of environmental things, and it's moving things to make them work better over time. It tries to move as little as possible, right? But it also tries to make the system work really well. And we've rewritten this twice, and it's a really sort of, it's one of the kind of core cool aspects of what we do, I think. As we have evolved the product, we have revved the storage system, including the on-disk layout, I think about 20 times.
Whoa.
It's a remarkable thing with scale out, right? That you can actually go and take a node offline and rewrite a bunch of its file system and then go and do things. We're very careful about how we do it, obviously. We test like crazy, and we're very, very cautious about the way that we add fields, right?
I
to
lived
minimize
10 years
the
with
amount.
3 versions. I don't how you can do 20 in
Many of those changes are super small, right? They're adding fields predominantly.
Yeah.
One of the other aspects of things is, unlike more traditional disk-based file systems where there's a really strong incentive to keep metadata directly adjacent to the data, we have a fairly high separation of those things. And so we can rewrite tons of the metadata, right, leaving the data in place on the system. And that's ended up
That
being...
makes that transition so much easier.
That's ended up being a really valuable aspect of the...
And I'm a firm believer that data layout is destiny, so having that flexibility
is important.
Yeah.
So one of the ways that in our first version of the system, as a way of sort of characterizing this is the evolution of this, in the first version of the system, we actually, these were shared nothing devices, and we implemented a bunch of functionality at kind of that level, right? Things like tiering were kind of like left to the devices to figure out. And it actually ended up being like a bad idea, right? Like it worked, and the system works quite well. Like I maintain that this was a great first round idea, and this is one of the examples where I'm going to tell you about experiences that we've had evolving a product, right? But they end up being kind of tied together, and there are better optimizations where you move just the high performance data around. And so the way that this seems to be evolving inside our system is effectively that inside the storage system, you have the sort of the file system level addresses that map down onto logical, and these map down onto global, physical addresses. And this is weirdly, I could have said this probably about many other storage systems, like at any time in history presenting, right? In some ways you can think about, this is a file system, a volume manager, and an aggregate level thing, right? Except that they're very different, right? In our world, we have this like global notion of where all of the data lives, and this thing is able to move that around. And so we have reverse indices at this level that let us do things like respond to failures or move in response to performance needs, right? At this level, you implement things like allocation and snapshots. And so moving things like allocation and snapshots up here means that you can avoid a lot of the contention that you might have historically had down here, right? So I can allow a core to have a range of logical address space that it can allocate writes into, and it doesn't have to go ask anyone else to allocate space for it. It ends up being a really, really significant win at these types of speeds. Right? Similarly, snapshots can kind of happen on that core, right, with those address spaces without having you to reason about all these lower levels of the system. And so this is something that we've been moving toward progressively over time. And I think, one of my goals will be that next year when we do this session, that I'll go into a whole bunch of details on where we've ended up with this stuff, because it's been a really exciting aspect of the system to see evolve. Anyways, let me close this session. As a quick summary of points, first of all, right, this idea, and as I said, I'm totally guilty of making this claim in the past, that I'm just going to borrow the techniques that worked for Facebook and Amazon and apply them in the enterprise, is actually not very accurate, right? It's distracting, right? You really need to think about these scales differently. Yeah.
If you've got one application, it's easy to put resiliency at the application layer. If you've got 1,000, it's really hard.
Yes, for all of these reasons, the interfaces and the placement and the scale. All of that stuff that I just told you about the media is really to emphasize a couple of sort of like simple points. That first of all, storage designers have a tough go of things today. These systems are going to take a while to really mature, to take full advantage of what they have, right? And I think that we're well along the path to getting really, really good performance and placement management in these environments. But the other thing is, the way that I'm talking to you guys, and I feel like you guys have a pretty high pain threshold, is the way that when we started as a company, I talked to customers. And there was a good lesson there, which is don't talk to most customers that way. We have a few that really want to go into the weeds that way. The thing that is absolutely true here is the extra bit, right? You have to deal with the traditional layout problems. You have to deal with these core level concurrency issues on performance, and you need to build that system in a way that adds nodes and retires nodes over time so it behaves like a service instead of like a piece of hardware. And by the way, the customer doesn't want to know about any of it, right? The system has to keep all of that stuff out of the way, right? In a recent executive briefing that we did, a large enterprise customer came in to the office to be briefed on things. We've been talking to them for months already, and the one demo that they asked to see was us adding a node to the system. And the reason that they wanted to see that, right, and to see the system rebalanced during our meeting with them, was that they were not just pricing per gig, right, without data reduction. They have no time for any of these sort of like weirdnesses, right, these large enterprise environments. They were also pricing operationally around the amount of full-time storage administration that was required for the box. And the hypothesis that they had was that it should be 1 day a week, not a full-time person to manage the system. And so that was the example they wanted to see. They wanted to see that they could add a node and that the system would scale out without a whole bunch of planned migration to go and deal with that. And so that's kind of the benchmark that we hold ourselves to.
Is that scaling out element when you're adding additional nodes, is that tied to your data locality kind of concept as well? So as you're adding additional nodes, you have some concept that actually we want to rebalance and keep some of this data.
Exactly. So one of the things, and this is actually a useful difference between both scale and building with disks, that in a lot of historical scale out storage work, you didn't just erase your code, but you did things like consistent hashing, right? So you had a hash function that you'd use to spray the data, right? And so it would allow you to not have to think about which nodes you were working with. This is a lot of initial object stores were really based around this idea. The nice thing with that is that it allows you to very cleanly scale up, right? Because you just go rebalance the virtual addresses in the hash function and you can move stuff around. It completely throws all object locality, data locality out the door, right? You've lost that by definition. And as we move into things like the Docker support that I talked to you later, the value of onboarding compute is putting it next to the data. And if the data is sprayed everywhere, I've lost to begin with, right? And so that's absolutely something that, so we try to keep very explicit models of where data lives and the ability to add a fine granularity, move it around, but keep locality.
And is there an additional way to kind of manage that from an administrator perspective to give logical kind of areas where your storage and your compute
Yes,
sit?
we're increasingly exposing that. So the first example of the way that we expose that locality is the new version of this thing has actually programmable rules to set those policies. And one of the rules that we've been prototyping and that I hope is going to make it out later in the year. This new version of the controller is just going into our release that's coming out in a couple of weeks. But one of the versions of these rules is one that's actually aware of the ESX to VM mappings. And it moves the VMDKs that ESX hosts are using to be co-resident with where the connection terminates. You can kind of think of it as like DRS on the storage side, right, where the storage system is adapting to the live migrations that are happening above it, right? And so the bulk of your accesses don't take any additional hops to go and find things in the storage system because they're always local to the node that terminates. Right? So.
And does that also impact in terms of resilience as well then? So it can say, well, I'm going to keep a copy of the data
Absolutely.
close,
So
but I'm going to keep another one as far away as possible.
That's totally true. So we have a notion of fault domains in here, and this has to obey those fault domains, right? And so you can set those policies on replication. One of the things that's actually interestingly different across customers as you get into rack scale is some of them want replicas within a rack, right, to reduce east-west,
Yep.
and some of them want at least one replica, right, that is non-rack local. Okay.
So you think from a customer perspective, with the OpenFlow SDN, locality wouldn't be as much a concern, but when you provide Docker support on the system, that's where locality becomes
That's suddenly
more
where it
important.
comes into play, absolutely.
Yeah, if it's
I mean, one of the other facets of that aspect of locality is in some of those sort of hash and spray, let's call them style systems. In many of them, you have to buy into the block size very early, right? You choose like a 4K block size,
Right.
and so if you're absorbing like 64K writes, and you suddenly have to divide them into, 8 or 16 subcomponents, right? The amplification off the back is problematic, right? You can never recover locality again there. And so even though you have wide switch bandwidth, you're still sending a ton of requests across the rest of the system, and the controllers take a lot of load. Right? Whereas with this, we can absorb the 64K write and just place it.
But this is all an argument against data deduplication as well, because two pieces of data from two completely separate systems that generate the same hash
Yes,
can only be local to one of them.
It is entirely possible to go too far with the dedupe stuff. It's one of the things that in our prototyping we've been like putting in thresholds against, right? Like, so you shouldn't dedupe gold master type stuff, right? You actually want to duplicate it, right, in some situations.
Wow. So just a couple of years ago, we were at, you should dedupe because Flash is really, really expensive. But now Flash isn't really, really expensive, it's only expensive. Time to rethink this whole thing yet again.
Absolutely. No, and I would go even further with that one, which is to say that a few years ago, Flash was really expensive, so we were deduping. But also, there was a strong argument to do inline dedupe because of wear, right? Like it was, you want your devices to live longer, so you would be crazy not to do inline dedupe. And the reality with a device that's warranted for 5 or 10 rewrites a day for 5 years is, like, why would you add any work on the data path, right, that you could defer if what you really want is to save space later, right? And so there's arguments to be made on all sides of this stuff. Okay.
We live in interesting times.
Okay, so I'm going to start. We're at 10:44, so I think I'm okay in terms of time here. I'll probably do this one relatively quickly. Is this an okay level of conversation, you guys?
But before you jump into that, can you go over a little bit about what you're doing for failure domains or what level the customer might be able to pick?
Absolutely. So we, by default, do 2 replicas in product. It's tunable up to higher degrees of replication than that. We set replica domains to always be on completely independent power supplies and links, and preferentially keep it onto separate chassis. As we scale across racks, some of the work that's going on right now is to expose that topology as well into the failure domains. The logic for stating those failure domains is totally programmatic, and so it's really just a matter of like coloring the nodes that you have.